Okay, thank you, Clement. And thanks to the organisers for the invitation and the opportunity to be here. I should just correct things. I think probably because my web page is out of date, I'm no longer director of the centre. Someone else took that over. Culver Dougal took that over a few years ago. And I'll say more about the history of GAP later, but I wasn't the founder. I've been involved with it for a while now, but the credit for initiating the project belongs to other people. I should correct two more of my own mistakes. I don't know how many times I looked at this slide while I was preparing the talk, but typos still crept through. And I also made the cardinal error of not checking when I got to the end of writing the talk that the title I'd written down at the beginning was still correct. I'm in fact not going to say a great deal about applications because by the time I'd finished covering the other things, I had what I reckon would probably be a 2-hour talk. Okay, what am I going to talk about? So, I'm going to say, I'll explain what I'm trying to do. I'm going to say a bit about computational group theory. My brief was to talk about computational group theory in a 2-hour tutorial, which really is, you know, it's a huge subject. It's impossible to cover it in a 24-year lecture course, let alone a 2-hour tutorial. So I'm going to try and give a flavor. I'm going to take a sampling of some interesting things, some of how what the subject deals with and how it goes about it, some of the issues that arise, some very old ideas and problems and some rather newer ones. And one of the things I want to extract from that is the special features of the subject that impact the design of the software. So GAP is a software system. GAP version 4 was released 21 years ago on Wednesday, I believe. July the 18th, whatever that is, 97. The first public release of GAP is a little harder to define because it predates widespread adoption to the internet, so it's really the first point at which some visitor to our campus handed a pile of floppy disks. And that was probably, Alexander, you haven't, I mean, really just... Okay, but so, yeah, GAP as such goes back perhaps 10 more years before that. Anyway, I'll say a little about that. Now, also, a little more recently, 20 years ago, at ISAC in 1998 in Rostock, was anybody there? Okay, not many. That's good, because I gave a talk then about the GAP4 design philosophy or aspects of it. I'm going to review that talk, see how the ideas then have held up, say a bit about some of the things that have changed since then, some of the things that in hindsight aren't looking so great. And then I'll talk about more recent developments still in the systems framework really, in trying to build a version of GAP that lets you exploit modern multi-core computers, our trials and tribulations. Okay, so that's the plan. I think, no, I'll say what computational group theory is first, and then I'll cut to an example. So, the design, analysis, and implementation of algorithms to compute properties of groups. That's, you know, the canonical definition. That's what you find on Wikipedia or somewhere. Groups should be read in a broad sense. The same methods, some of the same software, some of the same design philosophies have proved effective for a lot of things that aren't groups, like semi-groups and Lie algebras. The general point here being that these are rich structures where you can define them by giving a fairly small amount of information, but the structure is very large and the properties of it have to be extracted in fairly indirect ways. The algorithms both use and apply to problems in still broader swathe of mathematics. In order to do computational group theory today, you need algorithms from number theory, you need good finite field linear algebra, you maybe need exact linear algebra, you need some commutative algebra, some Grosvenor basis, and so on. It's a subject with a lot of history, as I've already hinted at. See, the history goes back a lot further than the origins of gap. There are recognizable, there are papers from the 1930s, if you ask some people even from the 1900s, which are recognizably algorithmic papers. They tell you how to do elaborate, in some sense repetitive computations to achieve the kind of results we're going to see here. And there are reports of people actually at St Andrews in the 1930s, during late 1930s, doing these computations. For those of you who know, I'll come back to this coset enumeration of anything up to a couple of thousand cosets on huge rolls of wallpaper. That was the only paper they could get in sufficient quantity, taking presumably weeks for teams of people to get a result that could now be computed on your wristwatch in 1 millisecond. But the paper, the algorithmic origins of this subject go back a long way. There are some fascinating papers from the heroic age of electronic computing, the sort of 1950s, where every computer was different. The idea that there might be a programming language that you could write a program in that would run on the computer in Cambridge and the one in Manchester is insane. They were different computers. They had different opcodes. You had to put different numbers in the memory to make them do things. But people like John Leach were doing group theoretic computations. There's one spectacular example on a machine which had 1,000 60-bit words of memory, I think, total. And we're still able to do elaborate coset enumerations. For reasons that I'll explain in a minute, or at least hint at, or give my views on, this is a subject where the software became integrated comparatively early. As early as the early 1970s, people were talking about and starting to put together a computer system that would do lots of group theoretic calculations. That was the idea at the time. And the first such systems that had any real wide use or life came into being in the later 1970s. Apart from mathematicians wanting to know things about groups they happen to have, something that turned up rather later is that this is a subject which has connections to some fundamental properties in complexity. I'm not going to say a lot about this, or anything about this possibly, but it was the motivation for another group of people coming into this work in the 1990s. The graph isomorphism problem, some of you will doubtless have heard of, depends, the question, polynomial time algorithms for that solve that problem for large classes of graphs that don't have certain unfortunate properties, are essentially group theoretic algorithms and depend heavily on group theory. It's by now a subject on which there are several books, thousands of papers, many millions of lines of software. So, as I said before, I'm not going to be able to cover, in any sense, all of it in a 2-hour tutorial. So what am I trying to do? I'm trying to give a feeling of the distinctive flavor of the subject on the assumption that most of you, at least, are people with a sort of computer algebra, symbolic computation background, but not computational group theory. So I'll try to give an idea of the ways in which it feels a little bit different from traditional symbolic computation. Explore how that impacts on the system design, and report on some recent developments that are mostly on the system side. Okay. Now, let's see if I can make this work. So, continuing combination of the relatively ancient and the modern. So, in, as far as I can see, 1993, Martin Schoenert, who I'll probably mention again, was the technical architect of GAP4, but he wrote a demo for the previous version, GAP3, in which he analysed the group associated with the Rubik's Cube. And I'm going to take a bit of, a version of that demo, or something similar to that demo. I'm also showing off something which is shiny and new, which is the Jupyter kernel for GAP. So, for those of you this is a Jupyter worksheet. You can see I'm using it in a web browser. We'll see some of the kinds of things you can do with it. But finally, we have at least a test version of a new interface. Yeah. Many of you will probably have seen this, but the Rubik's Cube famously came and said there were more than 3 billion possible states, which is definitely true, as we'll see in a moment, possibly a bit of an understatement. Okay, so we have to turn this into a group theoretic problem. Many of you will doubtless have seen this or thought of it or come up with it yourselves. There's nothing difficult here. So we number the 48 little... Actually, have people seen Rubik's Cubes these days? I didn't bring one, but if anyone hasn't, this is a plastic, this is an actual photograph, more or less, of a plastic cube. You can rotate any of the 6 faces, and these little squares get carried around with it. So there are 48 squares, not counting the ones in the middle of the faces that never go anywhere. And the first thing we're going to do is just number those. That's how we number them. And then with a little bit of care, we can write down what permutation of those 48 faces you get by each of the 6 fundamental moves on the cube. You only actually need 5 of those moves, doesn't matter which 5, but anyway, with all 6. So that gives us this. So far that was manual work. Okay, now, let's see if this is going to play. Okay, so this is input to gap and output from gap. We've made a permutation group. Okay, haven't done anything yet. Let's see just how many possibility configurations there are. Okay, there's the number. It took essentially no time. This is what? Okay, I don't know what that was about. This is actually being computed live. There's no man behind the curtain here. There's a gap session somewhere in the background doing this computation. You saw that took basically no time. Well, it's definitely more than 3 billion. Anyway, integers, as everyone, group theorists will know, are naturally written not in decimal, which is generally unhelpful, but as in their factorization as product of primes. So here we are. 2 to the 27, 3 to the 40, okay. Now, let's skip ahead for a minute and just ask gap by a reasonably naive, I don't know what's going on there, move to actually solve the cube for us. So, how am I going to do that? Well, I want to know what sequence of the generators I have to use to achieve any particular move I'm interested in. So I'm going to take a free group. If you, as you've done the group theory, this is familiar. If not, the free group is just the group of sequences of these letters. Multiplication is concatenation, and you can invert a letter, and inverses cancel. So I take a group homomorphism from the free group to the cube group, mapping each of these letters to one of the permutations I wrote down. And for reasons to do with the fact that this worksheet interface is still a beta test, I have to print it in a slightly weird way. Okay, so we make another group with 6 generators, this time the free group, and we get a homomorphism that maps these letters to these permutations. Okay, so far not very interesting. But now we can use that homomorphism to convert patterns, moves that we're interested in, or the elements of the group, so patterns we'd like to achieve, back to sequences of moves. So here I've taken the flip, the move that just flips all of the edge pieces of the cube and leaves everything else where it is, and take a pre-image of that under the homomorphism. Okay, and there we are. So that's a sequence of moves that you can read as a set of instructions to achieve the flip. Front, right, top, inverse right, inverse front, inverse. What's going on there? It's annoying. Anyway, I can check. That turns out to be of length 130, which is hardly record breaking. You can do it in 20, but it does work. And this is, taking a very generic sledgehammer to crack a very specific nut, and it doesn't fall into the nicest set of pieces. Okay. So we can do that. Now we'd actually been Mathematicians like to know something about the structure of this group, so we can basically just ask GAP to tell us. This is a composition series of the group, and the labels on the lines are the factors, so there's an alternating group on 8 points here, and cyclic group of order 2. So there's an A8, there's an A12, and there's a bunch of cyclic groups of order 2 and 3, and those are the composition factors. Okay. Now, today we can just do that. We can read off pretty much anything else we want. In the original calculation, in the 1993, that was still a relatively hard calculation, partly because the algorithms weren't as good, and partly because the computers weren't as fast. And to do that calculation directly and without randomization, without any possibility of error, was actually relatively difficult then. So also we might want to understand how this group relates to the cube a bit. So let's just carry on playing with GAP, dig into this a little more. So we've got a permutation group. The first question you ask for any permutation group is what are its orbits? In other words, how does it mix up the 48 points it permutes? And here they are. There are 2 of them. Not surprisingly, you can't move a corner piece to an edge position or an edge piece to a corner position. But it turns out you can do anything else. So now, if we're carrying on sort of digging into this, we can do something which is interesting because it's a very general technique. So this whole group is still quite big. We've still got, at this point, we've still got all the 4 times 10 to whatever it is, 19. It's the group, which is a bit. So we want to try and break it into pieces. And one way we can break it into pieces is by looking at how it acts, in this case, on one of the orbits, on the corners, and separating that away from everything else. So I'm taking the action of the cube group, on the first of these orbits, which contains all the corner facets, and see what comes out of that. Okay, so we get a much smaller permutation group. And just checking, works on 24 points. Those are the 24 corner facets. Yeah. We can ask, are those corner facets, so we know that it's transitive on the 24, but we can ask, is there a partition structure that's preserved? Is it imprimative? Yes. The 3 facets that are at a particular corner of the cube stay together. You can't get one of them onto one corner and one of them onto another corner. No huge surprises here. So we get 8 sets of size 3. We can act on those. And we find that we've got the whole symmetric group, and GAP actually recognizes it as such. I'm probably going to. We can carry on digging into that. We can find out what happens to the things that don't move those blocks around, so that leave all the corners where they are, but maybe twist them, and discover eventually that we can do all but one of. We can do any combination, any twist of 7 of the corners, and that will tell us what happens to the 8th one, or whatever we like. We could now carry on and explore the edge group and other things, but it's enough for now, I think. The flavour of one kind of exploratory computation that you can do in computational group theory. And this is, this is in no sense a challenge or difficult computation, but it gives a little bit of a flavour of what happens, and it sets up something interesting later. If anyone wants an exercise, I'll make all the files for all of this available after the talk. You could explore the 4x4x4 cube, or slightly more interesting, the 3x3x3x3 Rubik's Tesseract, something that the toy company strangely never sold. Okay. Onwards. Maybe. Hello? Ah, here we go. Right, so what is a group that we want to compute with it? Well, textbook definition of a group is well known. It's a set with a binary operation which obeys these three axioms. The operation is associative, there is an identity element, and every element has an inverse. Okay, this, I imagine, no surprise. So this definition is very concise, it's mathematically very elegant, and for computational purposes it's utterly and completely useless. The problem essentially starts here. For any group that we would be interested in, we are never going to write down that set, ever. I mean, we just saw the Rubik's Cube group, which these days is a little five-finger exercise for any computational group theory tool, and that group has order 4 10 to the 19 or something. We're never going to write all the elements down. So, similarly, we're never going to actually see this multiplication operation as anything like a multiplication table, as maybe you might see it in the very beginning of a first undergraduate group theory course or something. That would be even bigger object to write down. So computational purposes, a group is essentially always going to be given to us, one way or another, as a set, usually but not absolutely always a finite set, of generating elements, and enough information to multiply them, compare them, and take inverses. So somehow or other I'm given these elements, and I'm given some program I can use to multiply them, to make more elements, to compare the two elements to find out if they're equal, and to take inverses. I may need the identity element if my group is infinite, but otherwise not. So you've already seen one example of this. I can specify a group by giving a set of generating permutations on a finite set. That's what we did with the cube. Multiplication is easy, although optimum cache-friendly multiplication actually isn't, but that's another story. Equality is just a memory is just literally they are the same data, and inverse is also easy. You might be given a set of generating matrices over some ring that you can compute in. Traditionally, this would usually have been assumed to be a finite field. Today, an increasing amount is happening with matrices given over infinite domains. It might be given to you, as we saw that free group, might be given to as abstract generators, so you've just got names for the generators, and some equivalence relation on words in those generators. So you're told perhaps a rewriting system, and if two things rewrite to the same terminal, then they're equal. Might be given in some other way. For the free group, for example, the equivalence relation is easy. You just cancel inverses. And again, that lets you do all the things you need to do. Okay, so that's your input. What do you want to know? Well, of course, it varies. Here are some things that people often want to know. If the group is, they'd like to know the order or cardinality of the group that's generated. Is it finite? Is it infinite? If it's finite, how big is it? Given another element of the same kind, another permutation, they'd like to know if it's in the group. If so, they might want that constructively. This is essentially what we were interested in for the cube. Given another permutation, is it in the group, so can that position be achieved? And how do we write it as a product of the generators? You might want to know, is the group isomorphic to another group? Or perhaps to some named group from some library. And there are a whole raft of algebraic questions you might want to ask about the group, and people are always coming up with more. So take some relatively elementary ones. Is this group abelian? Is it simple? Is it solvable? Is it polycyclic? Is it finite? You might want to find or classify elements or subgroups with some properties. So you might want to write down all the maximal subgroups, or find an element that, find an element that lies in each possible conjugacy class of the group, or find an element that maps this set to that one in permutation group. If you're not familiar with all of the terms here, don't worry about it. They all have definitions, obviously, but the real point here, and the thing I'm trying to convey, is that what's different about computational group theory from much, not all, but much of other symbolic algebra, is that we start with individual elements, generators, whatever, and all our computation is in reality going to be with elements or things closely related to it. If we're working with a permutation group, we might be computing with points or sets of points or orbits or partitions of orbits. But there's still things that are, and then we look at what individual permutations do to those. That's what we spend, that's what our computer spends its time doing. In permutation group computation, it spends its time mapping points through permutations and looking them up to see if it's already got them, things like that. But the questions we want to answer aren't like that at all. The questions we want to answer are high-level questions about the whole group. And it's the disjunction between those that give this subject its special feel. You have a lot of choices of how to get from what you're given to what you want to know. Because you're given something relatively small, often, 6 permutations. You want something relatively small, like an integer, or often just a yes-no answer. No, that doesn't help. Pointing this at the screen is not useful. You want to know, is it a billion? Is it simple? Is it solvable? But in between, you're going to have to find a route from what you're given, which might involve building some complicated data structure. It might involve, as we saw a hint of with that Rubik's Cube, looking at other groups entirely. We look at quotient, you look at quotient groups or subgroups. You find a matrix group that's isomorphic to the permutation group you first started with, because some bit of the question can be answered more easily in matrix groups. So that's really what distinguishes this from a lot of other things. You're not simply computing with elements or expressions or matrices or something. You're trying to answer structural questions using elements. Okay, so let me dig into one such question for a while, which is one of the great classic questions in the subject. I'm given a finite set of permutations on m points, and I want to know the order of the group they generate. Okay. Option 1, what would happen if you give this problem to a first-year undergraduate? Listing all the elements. In the worst case, that's super exponential in n. If your permutations happen to generate the symmetric group, or if an undergraduate is doing this on paper, if they make roughly any mistake at all, they will end up writing down all the permutations on n points, of which there are more than 2 to the n. So we don't want to do that. And ancient, relatively speaking, theory suggests a better way of approaching this. So going a few pages further into the first-year group theory course, we find Lagrange's theorem, which says that the order of any subgroup of a group divides the order of the group. So we can hope to get the answer we want as the product of the order of some subgroup and the index of that subgroup. We can factor the problem multiplicatively, and that's really nice. So our big edge over the semigroup theorists, most of the problems they have don't factor multiplicatively. You can say, okay, I'll split the semigroup into this bit and add them up, count them separately in different ways. But finding anything that multiplies is much harder. And in fact, we can recursively apply the same idea and factor the problem along a whole chain of subgroups. Okay, so let's see a little bit more about how we do this. Quickly, a few definitions. The orbit of a point under a permutation group, which I will write omega to the g, that's the set of all things you can get to by acting on omega. The stabilizer is the set of all elements of the group that don't do anything to omega, and I'll write that g sub omega. And to avoid death by parentheses and make my LaTeX slightly less nightmarish, I'll write g alpha beta for g alpha beta. So if I'm fixing 2 points, I'm just going to write them like that. And trivial, again, from the first few pages of the first year textbook, g omega is a subgroup of g, because if 2 things fix omega, then their product does and their inverses do. And its index is the size of the orbit. So if we can find an orbit and a stabilizer, we've made some progress towards computing the size of g. How do we go about doing that? In particular, finding the stabilizer. Well, it's a very useful gadget variously called the Schreier vector, the Schreier tree, or the Schreier graph, depending slightly on what you mean and slightly on how recent your computer science is. So the 1970s books talk about it as a vector and describe exactly which numbers are in which positions in the array. 1990s people tended to talk about it as a tree, which is actually the part of the structure used computationally. It's actually the spanning tree of a graph, and I'm going to include the whole graph. So anyway, it's an edge-labeled directed graph. Its vertices are all the points that you act on. And for each generator, so X are the generators, and each point, we're going to have an edge that tells us how that element acts on that point, which I will label with the generator. So in this case, I've got a permutation group generated by these two permutations. So the edges corresponding to this generator are labeled by being drawn in red, and the edges corresponding to this one are labeled by being drawn in green, except that these have somehow ended up blue. So there are 4 points, 1, 2, 3, and 4. The red generator maps 1 to 2, 2 to 3, 3 to 4, 4 to 1. The green generator maps 1 to 3 and 3 to 1, and leaves 2 fixed and leaves 4 fixed. Okay. Yes, that's a thing. Why do we want to know? Well, because it turns out to be an effective way of computing orbits and stabilizers. So there's a theorem, which isn't hard to prove, that if you take the cycles of this graph and read around them, the labels you get generate the stabilizer. If you think about it, for long enough, it becomes obvious. So we can do a breadth-first search of the Schreier graph, starting at the point we were given, and find all the points that lie in its orbit. So we're only finding, in principle, there might be a whole lot more Schreier graph out there of points not in the orbit, but we don't really care about those. They're what a computer science would call the discovery edges in this search. So the ones along which we find the new vertex for the first time. Those necessarily form a spanning tree. We find a new vertex for the first time, and the graph consists of everything we find. There's nothing to say there. And we can store the tree by noting on each vertex the label of the discovery edge. So if we discover vertex 2 using the red generator, we remember that fact. That's all we have to remember, because we can apply the inverse of the red generator to vertex 2 to find out where we came from. And whenever we revisit a vertex, so we discover a vertex we've already seen, we've discovered a cycle, and so roughly speaking, we've discovered a generator for the stabilizer. So here is what you get if you do that on that same graph. So the bold arrows here, the thick ones, make up the spanning tree. So 2 was discovered from 1 using the red edge, 3 was discovered using the green edge, 4 was discovered from 3, and that's everything. And for a couple of sample cycles, so one of the cycles is here, we go from 1 to 2, around there, and back. We read the label on that, we read red, 1, 2, 3, 4, green, red backwards, multiply those 3 permutations together and we get 2, 4. Here's another cycle. So we do red, red, green. That's this. We get 2, 4 again. That is a bit of a problem with this approach. We do get a lot of repeats. And if not actually repeats, in bigger examples, we get a lot of redundancy. However, that gives us an algorithm. So based on that, we could produce what we might call the Schreier algorithm. I'm not sure. I don't believe Schreier ever stated it as such, but it's kind of the part of Schreier-Sims that doesn't involve the things that Sims invented. To determine the order of a group, pick any point, compute the orbit and generators for its stabilizer, recursively compute the size of the stabilizer, and return the size of the orbit times the size of the stabilizer. Okay. It's an algorithm for computing the order of a group. The biggest problem with this is that if you think about the graph algorithm for a moment, the number of generators you get for the point stabilizer is the number of generators of the group minus 1 times the number of vertices minus 1. Because for every vertex except the one we start from, we will reach it at some point using every generator. And all but one of those will be non-discovery, so they will give us cycles. That's, in general, quite a lot. We were interested in solving problems where this might be millions, and, well, we might be given, if you think about the recursive call, we'll certainly often be given a lot of generators. Most of those generators will be redundant. They will not actually be necessary. If you pick a few of them at random, it will probably generate everything you want. When we repeat this in the first recursive call, we have that many generators for G alpha, so we have that many minus 1 times the size of the orbit of beta, minus 1, generators for G alpha beta. This gets bad quite quickly. And as we saw in that very small example, they were literally duplicates. We got the same generator twice. In larger cases, that's not what actually happens. The third generator you get is the product of the first one times the second one to the 17th power, and then the fourth generator you get is some horrible word in the first two and so on. Okay, so how do we do better? So this is really Charlie Sims's contribution to find a better way of organizing this calculation so that we don't get all the redundancy. So we want to know in order to explain Charlie Sims, I have to digress slightly and explain how we solve a different problem. So this is the membership testing problem. We're given a permutation, and we want to know if it lies in G. So we can run Schreier's algorithm and keep all the data structures. And then we look at the original point alpha, and this element pi. We see where it takes alpha. If it takes it to somewhere that's not in the orbit, then, well, alpha to the G is everything you can get to with G. So if alpha pi is not in alpha to the G, pi is certainly not in G. So we can say so. Otherwise, we can use the spanning tree to read off a canonical element of G that maps alpha to wherever pi maps it to. Then we divide that off and ask, is that in the stabilizer? So this is a permutation which fixes alpha, and it may or may not be one of the ones that's in G and fixes alpha. So recursively, so we answer that question. Okay. This leads to the first really useful algorithm here, for most purposes, Schreier-Sims algorithm. So the idea here is that we mix these two things up. We're going to mix up our computation of all these subgroups with our membership test. So we're going to keep data structures for whatever subgroup we currently know about, initially just the identity element, of a point stabilizer, a two-point stabilizer, and so on. Whenever we find a new cycle in the Schreier graph, we immediately pass the generator that we get down to the membership test and say, based on what you already know, is this in the subgroup G alpha you've already got? And it will either say yes or no. And if it is, then we just throw it away. It's told us nothing. We've checked and there isn't another generator there, so we can move on. If it turns out not to be in there already, we've found something new, we update the data structures to reflect the new bigger group. This is usable for reasonable degrees. The problem now is that it doesn't keep all these redundant generators, so it doesn't have to use them to construct two-point stabilizers and three-point stabilizers, but it does still have to check that they're all redundant. And that becomes extremely boring. It will spend most of its time producing Schreier generators and discovering that they lie in the stabilizer you already have. Not so good. In other words, what happens if you do this computation is that the data structure normally reaches its final form almost immediately, and then you spend ages proving that actually it is in its final form. I say normally here, there are some perverse cases, but essentially that's what happens. Okay, before I go on and talk about how we can improve that technique still further, let me digress a little into one of the sort of philosophical points I want to take out of this, which influences the software design. This is the point that there's no canonical representation for many things. So this whole set of Schreier graphs, the data structures that relate them, all the labels on edges and vertices and annotations and whatever, that whole collection of structure is called in GAP and other contexts a stabilizer chain for the group. It's a chain of stabilizers of 1 point, 2 points, 3 points, 4 points, whatever, and a whole bunch of data structures that go with them. It's a great thing. You can do lots with it. It's the basic data structure that practically every permutation group computation you ever do starts with. And it reduces many of the things the user cares about, algebraic questions about the group, to questions that you can ask about permutations, points, and sets of points, which is really our game. So it's key. It's a key device. But it's not canonical. There's no particular sense that a group has a the stabilizer chain of the group. There are loads of stabilizer chains. It can depend on what generators you started with, what choices of points you made to stabilize, what order you happen to discover the generators of the stabilizer in, lots of things. And that's a very general thing that happens here. So I chose to give you the cube group generated by 6 generators. I could have made some trivial changes to that. I could have chosen to turn the faces in the opposite direction. Still generates the same group. It doesn't matter which way you turn the faces of your cube. I could have chosen, instead of starting with those 6, just to start with 5 of them. It's easy to see, if you think about it for a moment, that you can hold one of the faces still and rotate the other 5. It doesn't really make any difference. Or I could have even started with 2 or 3 much longer and more complicated moves that just happen to generate the whole group. So in general, the same, not just an isomorphic object, that's certainly true. I can have the same group in some completely other form. But the same group can be represented by quite different data. And that can happen in lots of different ways. If I have a conjugacy class of a group, I'll represent it by remembering one element in it and the fact that it's a conjugacy class of this particular group. And which element I have is more or less arbitrary. And this is very common. It happens all over the place. Because we're interested in structures, but we have to represent them by elements. And that makes a few things that are commonly easy in most other programming language contexts or even symbolic computation contexts really hard in GAP. There are plenty of objects in GAP for which testing equality is time-consuming. There are some for which it's actually Turing incomputable. So there is no algorithm that guarantees to tell you whether this object equals that object or not. That means a lot of nice things that people take for granted in programming language these days are tediously hard to do. If you want to have GAP objects as indexes to a dictionary in the way you might in Python or any other systems, first thing you want to do is hash them. But if you give an equal but differently represented object as the key, you want to get back whatever you put there in the first place. So your hash function has to respect equality, it can be almost arbitrarily hard. So this is just one of the things that can influence the software design. I'll come back to some aspects of this. Computing a canonical one is sometimes possible, sometimes not. And even though it's possible, it might be bad for other reasons. This isn't always a bad thing. It means that some things that people would like to do turn out to be tediously hard. But it also means that we can choose which stabilizer chain we want. Our group doesn't have just one stabilizer chain, it has lots. And if I don't like the one I've been given because it's not suited for some computation I want to do, I can always make another one. But yeah. So again, it's this mismatch between computing with a structure, or very often actually not even the particular structure they were given. One of the things that you discover quite quickly if you try and do computational group theory, and probably most other kinds of computational mathematics, is how amazingly sloppy mathematicians are with terminology. So a mathematician will say this group is A5. The alternating group on 5 points. Depending on the context, they might mean it actually contains the permutations of 5 points of even sign. Or they might mean it contains of the 5 points 1 up to 5. Or they might mean it contains the permutations of some 5 points, but not those 5. Or that it's just isomorphic to that group, or something else. So sometimes figuring out what question, matching up what the system responds and what the mathematician asks is quite difficult. Okay, back to the algorithms. Let's speed up a little bit. So the next step up from Schreier-Sims is random Schreier-Sims. So instead of computing all the Schreier generators, we start by just picking some at random. So instead of doing a systematic exploration of the graph and computing all the cycles, we probably build the tree, but then we just pick random edges off the tree. Those give us cycles. Compute those, pass them down to the next level, gradually fill up, stabilize the chain. And we stop doing this when, well, if we're lucky, the product of the orbit length, so our estimate for the size of the group, reaches something we already knew. If someone told us this group isn't bigger than such and such, that's great, we can stop. The riskier approach is to say, well, nothing has changed for a while. I've been computing random generators, and in fact, if I've been good, I've done it in a particular way that's due to Babai and Koopman and some other people. And I've computed enough of them that I can be sure with 99.9% probability, or whatever I like, that I've actually got them all. If you're lazy, you just say, well, nothing's changed for the last 5,000 random generators I produced, so it's probably time to stop. But even so, you have at least a controlled probability of error. And now you have to go off and find some other way to verify that the result is correct. Okay. Yeah, said that already. What this gives you for the important family of groups, they're called small base groups. There's no about these things. It doesn't really matter. Monte Carlo, read this as soft O of n. And what that means is big O of n times some power of log n. Basically, at least for along the computational group theory, it's a sloppy, unlike the linear algebra we were hearing in the previous talk, we don't count the powers of log very accurately. So big O of n times some power of log n. And I said for an important family of groups, groups outside the family can be dealt with in other ways that I don't want to talk about just now. What we like, oh yeah, now I said Monte Carlo, so that's with bounded probability of error. So I can specify the error probability. The lower I want the error probability, the higher the constant in here will be, but nothing else changes. And I'm fine. Las Vegas says I have a specified probability of failure. If I get a result, it's correct, but with a certain probability, I'm allowed to say no. Or to think of it another way, the running time is allowed to extend in a sort of exponential die-off kind of way. So it may not always run in that time, but the probability that it will need longer is very small. And that's what we'd like. To give an idea of what an achievement this is work of a lot of people. I'll say a little bit more about how you get there in the end in a while. N, remember, is the size of the permutation. So to multiply any two permutations is going to take big O of n. It cannot be faster than that because we have to write down the answer. So this is doing the whole calculation in no more than log n to some power permutation multiplied. So it was an impressive achievement. Okay. Now, I'm conscious that I'm getting through time quite fast. Our problem now is that we're given our permutation group again. We're given a stabilizer chain that claims to be a stabilizer chain for G, and we want to check that it actually is, which amounts to checking at each level that the thing we're given as a stabilizer of a point actually is the stabilizer and isn't some subgroup of it. We know the result's probably right, so we don't have to worry too much about what we do if it's wrong. If we discover that it isn't right, we can just throw up our hands and go around and try again. Then with G, it's easy. There's a whole bunch of ways I don't want to talk about, again, going back to Charlie Sims in the 70s, to get away with checking fewer Schreier generators, but still tediously many. And there are two other ways, which are what I really want to come to here. So one is an algorithm called Schreier-Sims, also quite old, which I'm going to say a little bit about now. I'm looking at the time, not that much. And the other is black box group recognition, which I'll come to in a minute, which is much more recent. So, actually, thinking about the time, I'm going to skip the Schreier-Sims. I'm not going to get to other things I do want to talk about. The idea here is that you can use the theory of finitely presented groups. I'm sorry, I'm just trying to find my way forward to where I need to be. Yeah, okay. So, yeah. The only thing really I want to say about the Schreier-Sims then is, given the time, is that it draws on techniques from a completely other area of computational group theory. So Todd-Coxeter algorithm is a core algorithm for dealing with a finitely presented group. You can think of it as a kind of specialization of non-commutative Grosvenor basis. It has the same problem, that the problem is actually showing unsolvable. But it turns out that it's still, for many cases, one of the best practical ways of verifying a stabilizer chain. You can extract a presentation for the group and work generators for the stabilizer and check that the presentation is enough to guarantee that the index is correct. For those of you who know some group theory, those who don't worry about it. As I say, except to take the point that you're drawing on completely other areas of computational group theory to solve what looked like a nice combinatorial problem about permutations. And that's going to get a lot worse. So Schreier-Sims doesn't give you any useful complexity, any formal complexity bounds, it just works sometimes. So we're back to the quest for Las Vegas nearly linear time. You've got a stabilizer chain, you know the stabilizer chain is correct. So if you have a stabilizer chain and know that the stabilizer chain is correct, then it turns out you can compute, and this is a huge amount of work by a number of people, most in particular I'd name Achos Sheresh, but a lot of other people were involved, compute many properties of the group in soft ON time. In particular, you can compute a composition series. That breaks the group down into factors, which are simple groups. We saw the composition series of the cube group on the worksheet. So we could appeal to the classification of simple groups, so get out the really big sledgehammer, and just say, well, what could all these composition factors be? We have a list of all possible types of isomorphic classes of non-abelian simple group, or a simple group. So somewhere in that list must be each of our composition factors. If we can identify them, then, well, we know how big they are. If we know how big they are, we multiply those up, we know how big the whole group is, and then we're happy. That will verify our stabilizer chain, because the order we computed from the stabilizer chain will match the order that we get from the composition series, and we're happy. So we want algorithms to identify simple quotients of permutation groups. And we need to be able to do that with hardly any permutation multipliers. We've got logarithmically many permutation multipliers that we're allowed. So identifying groups, we have to do the identification mainly just by tracing things through the permutations, not making new permutations, and studying properties, when points get mapped back to where they started from and so on. Okay, this essentially turns out to be a version of, or something close to something that was mentioned by Dave Benson in his thesis in 1982. He described it as the group game. So the group game is a game where your adversary gives you names for the generators of an unknown finite group. So we'll see an example in a second. You're allowed to ask for the names of any products or inverses of the elements you've already seen that you like. Two elements are equal if and only if they have the same name. If you can have a variation where you have to ask, but it doesn't really matter. And your job is to identify the group up to isomorphism. So here's a very short game. Your adversary, who speaks in red, says to you, E1, E2, those are your generators. I say, okay, I'd like E1 times E1, please. That's E3. It's different. It's an element. It's different from all the ones you've seen before. Okay, let's have E3 times E1. That's E4. E4 times E1. That's E1. Aha. So now I know that if I multiply E1 by itself 1, 2, 3 times, I get E... hang on, what have I done wrong here? Oh yeah, multiply E1 by itself 1, 2, 1, E3, E4. I think I've lost count here. I think there should probably have been one more step of multiplication here, E3 and a half. What I wanted to see was that when I multiplied E1 by itself 3 times, I got to E4, which was 1. I think, in fact, I've only multiplied by myself twice there. So pretend there were 3. Now I ask, what do I get when I multiply E2 by itself? E4, which I already know now is the identity. And on a hunch, I'll ask what happens if I multiply E2 by E1 by E2. And that turns out to be E3, which I already know is E1 inverse, E1 squared. Oh no, this is all correct. My apologies. Yes, there are only two multiplications to make E1 cubed. Duh. Okay, so that tells me that E1 conjugated by E2 is E1 inverse, and at this point I know what the group is. So it's not a game you actually win or lose as such, although I suppose you can make it that way by giving some bound on the number of questions you're allowed to ask. So this, as I say, was first described in 1982 in a more or less an aside in Dave Benson's thesis. It reappeared in the guise of the theory of black box groups about 15 years later, quite independently. So the people giving it then were a bit more formal about things. So a black box group is a finite set of bit strings. It's with two Turing machines, the multiplication machine and the equality machine. If your group isn't infinite, if your group is infinite, you're going to need an inverse machine as well. And the multiplication machine does multiplication. So if you give it x1 and x2 suitably separated by some standard symbol on the tape, it will terminate with a string on the tape which represents their product. The equality machine run with x1 and x2 on the tape terminates with either a 1 or a 0. They're just oracles, we don't really care. And it actually has to be a black box group and not just a black box magma, so I do want the group axioms to actually hold. Boring details. For some complexity results, I'm going to assume the existence of a couple of oracles. One is an oracle that can compute the order of an element. So if I'm dealing, for example, with 100 by 100 matrices, the multiplicative order of such a matrix, a random invertible matrix, will be extremely large. I don't want to have to compute that just by multiplying by itself repeatedly until I get to 1. It will take far too long. And in practice, if I have that matrix, there are much more efficient ways of computing its multiplicative order. So it makes sense to allow myself an oracle that does that more efficiently. In some situations, you also need to take discrete logs. And again, we just appeal to an oracle. And in a typical complexity result in this area, it will say, we can do this with so many calls to these machines, so many calls to the order oracle, so many calls to the discrete log oracle, and maybe a few other things. Okay, now, why does this relate to the stabilizer chain stuff? Well, if I give you a stabilizer chain for a small base group, I don't have time for the explain details here, but you can construct a black box representation of the group. This is, for those of you who do know, you just represent it as a word in the original generators and occasionally shorten that word. Operations take soft O of 1 time, which suddenly means you've got a lot more headroom. By working in the black box representation, you're now allowed order n group multiplications instead of order 1, or order log n. You've given up quite a lot. You can no longer look up points in your permutations or anything, but it turns out you can do more or less whatever you want. Same situation applies to matrices over a finite field. So now, remember what we were trying to do was identify all the composition factors of our group. So now we get to the question of representation of simple groups. And this is, here's the problem. Given a black box group, given by some generators, and which is known to be simple, I'll take a break in about 5-10 minutes at the end of this section. Tell me what simple group it is, that's non-constructive recognition, and find an isomorphism from the group you gave me to the standard copy and back. That's the problem, and essentially the solution is to write an algorithm for every infinite family of, well, take the classification of finite simple groups. The sporadic groups you can ignore because their order is big O of 1. This is slightly unrealistic for some of the bigger ones, but they're a constant obstacle. They don't relate to the complexity of things, at least. And then for each of the infinite families, you need to come up with an algorithm more or less independently for each one. There have been attempts to produce more uniform algorithms, varying degrees of success, but there are a lot of algorithms. It's enough to do Monte Carlo recognition, provided that you also know a nice short presentation of S. And thanks to Cantor and some other people, we now know those for everything. Okay. I'm going to skip over this. I'm conscious that I'm using a lot of time. We just very briefly give you a flavor of one of these algorithms. So I'm going to specialize completely and say I want to constructively recognize S13. So I've been given some black box group, and I believe that it's the symmetric group. I know symmetric group isn't simple, but the algorithm for the alternating group just has a bit more bookkeeping. I believe that it's the symmetric group on 13 points, and I want to try and get an idea of how we're actually going to recover that fact. So the first thing we're going to do is we're just going to search through the group until we find an element of order 22. And remember, we're working on the assumption that the group is S13. There's only a very small probability that if it isn't, if anything goes wrong during this process, we just throw up our hands and say, that can't possibly have been S13. There are a reasonably large number of elements of order 22 in S13, so this won't take too long. Now we take it to 11th power, that gives us an element of order 2. There aren't very many of those, so looking for it directly wouldn't have worked. Same sort of idea, we find an element of order 13, and we try conjugating our element of order 2 by powers of our element of order 13 until we get something where y to the theta k has order 3. So we're hunting inside the group for configurations of elements that suit our purposes. Here's one such. Now, a little bit of fiddling. We end up with 3 transpositions that share one point. So a configuration. Okay. So there are 3 transpositions, 3 permutations that just swap 2 points, and their configuration is like this. So each of them swaps that point with a different other one. And we're going to use that set of 3 elements of the group as a proxy for that point, the point that they have in common. And it turns out that if you have 2 such things, if you look at the orders of all the products, all 9 products, 3 things from one, 3 things from the other, they will tell you whether or not they're the same point. All the configurations where they are the same point, or all the configurations where they're not, have different sets of products. So now we can effectively collect the 13 different such triples representing different points. And then we've got the action of G on 13 points. We pick one of those triples, conjugate by any group element, and it will go to something which is the same point as one of the 13 triples and is not the same point as the other 12. And that tells us where that point goes under that group element. So now we can read off the permutation of 13 points for any element of our black box group. We number those points in some convenient way, and then given any element of S13, it's easy to write as a word of those permutations, which gives us the inverse homomorphism, and essentially we're done. Okay, that's a very quick sketch of one specific case for one specific group. The common theme that applies to most of these recognition algorithms, at least, is that you're discovering the geometry of the known simple group. So in this case, S13 permutes 13 things. What I'm doing is looking inside the black box group I was given to find 13 things that are placeholders for those. Exactly the same situation arises if I'm looking for a matrix group, a linear group or something. I want to find something inside the group which I can use as my vector space. Okay, almost done. So there's been about 2 decades of work on this. All black box simple groups can now be constructively recognized in polynomial time. The last ones were announced a few years ago. It's the work of very many people, including the mayor here. But perhaps the moving spirits are people who kept this going, who nagged people to do the cases that have been left out and so on. I'd mentioned Sir Eamon O'Brien, Charles Leedham Green, on a more theoretical side, Bill Cantor. It depends on a lot of knowledge of the structure of the simple groups, case by case. And apart from trying to give you a flavor of what happens, the moral of the story here is that we started with a very simple problem. We started wanting to know what these permutations, nice simple combinatorial things, given to you as probably arrays, so what the order of the group they generate. Or you might want to be able to test whether a particular permutation is in that group. Simplest question you can imagine. In order to do that with Las Vegas, the best known or possible Las Vegas complexity, you have to know an enormous amount about every single class of simple groups in the classification. The algorithms that you need to do some of those recognition problems depend on Lie theory, on linear algebra, on other things I probably think about, number theory. And that's a common thing here. So, okay, I'm going to skip most of the rest of this, I think. Yeah, this is where I want to get to, and I'll finish here and we'll take a comfort break. You can't isolate functionality in computational group theory. Maybe it's a feature of the nature of group theory, but to compute in a simple combinatorial structure like a permutation group, we found ourselves using finite presentations, the Todd-Cluxter algorithm. Again, I skipped over that, but that's happened. Constructive recognition, black box group techniques. You need linear algebra, cohomology theory, and a whole lot more. We depend heavily on randomized methods, even if we want a definitively correct answer. There's no deterministic algorithm that is reliably as efficient as the best randomized algorithms. And this really is the point that's going to leads me into the section I'll come back to after the break. You can't isolate areas of functionality. You can't even organize them into a nice dependency chain. You can't say, okay, first I build my permutations library, then I build my linear algebra library, then I build my something else library. You'll rapidly find that your matrix group code calls your permutation code, which calls your matrix group code, so it's one of the reasons, I think, why this was an area where integrated systems came up very early, and you don't see systems, as you do in some extent in algebraic geometry, for example, showing up as nice stacks of C and C++ libraries where there are low-level libraries and mid-level libraries and high-level libraries, and they all call each other in a nice orderly fashion. Okay, which leads me on to system design and issues like which I will take. So let's take a 5-minute comfort break, and then I will come back and we'll continue.
Okay, thank you. So yeah, it's time to maybe ask a few questions on this first part of the talk. So do we have any questions from the audience? So I had one. So you were at some point assuming you could use some array proofs, including one for discrete logarithm in O(1), which sounds like a strong assumption. So how is it realistic for real-life computations?
It's realistic because the size of the discrete log problems you get out of feasible sized groups are not that hard. So in real computations, you don't spend a great deal of time computing discrete logs if you use any reasonably state-of-the-art problem. In theory, you could, if you either used a very perversely constructed input or a ridiculously large one, you would end up spending all your time doing discrete logs. The problem is it comes down to recognizing essentially whether you've got a cyclic group or the direct product of two copies of the cyclic group, which depends on whether this is the same power as, I can show you can construct two matrices, but the reason it's not a practical problem is simply that it's hard to make the discrete log problem big enough for it to become difficult. Yeah?
This might be a naive question, but you say you need to be able to do almost everything well to be able to do it well. So what would be an example of something that you could just kind of skip over and still be able to get something out of this, or not have anything?
The Grosvenor basis in GAP is not competitive in any sense with any serious Grosvenor basis library. There are some extension packages that do link to better Grosvenor basis, but you do need a Grosvenor basis to do a few things in group theory, but you don't need a particularly fast one. That will be a typical example. You might want to use it. If you want to do something like invariant theory, then of course you need a good Grosvenor basis. But if you just want to do matrix groups, you do occasionally need one, but it doesn't need to be particularly special. Of course, sorry, yeah. So a base of a permutation group is simply a sequence of points where if you fix all of them as a sequence, so you fix all of them individually, there's nothing left. The stabilizer of all of them as a sequence is the identity. So a small base group is a group that has a small base. Small is usually taken as being big O log n. Any groups which are not small base are classified, and they have other structure that shows up in the permutation which you can recognize in other ways. So I'm essentially saying this stabilizer chain computation isn't going to go bigger than log n or a big O log n levels deep. Okay. Yep. I'm okay. I just want to go back to the.
Yeah, let's wait 2 minutes.
Yep.
Doesn't even have a polynomial type. I mean, it certainly doesn't.
You might be right, actually. Yeah, I was looking at
I think that,
Martin Liebeck's talk from the last Oberwolfach, but yes, you're right, that wasn't there.
yeah.
Yeah, okay.
And I mean, well, in some way.
I think all the other rank ones
Yeah,
are
that,
good.
I mean, well, actually, Akash and me, what we ended up with before Akash died is we have what we think is a polynomial type presentation. Not just, sorry, we have a small presentation, not just polynomial, but small in the sense as they use.
Yeah.
We just can't prove that it's a presentation.
Oh, I thought the small presentations were good. I thought they were good for everything. Oh.
You know, the twisted G2
Okay.
is the one which is not.
Right.
And that's, if you look at the Babay-Biot-Serish paper, they have that as an exception. And so
I misread the Liebeck,
Yeah, yeah.
Martin Liebeck's abstract
and
from the
on the
Wolfach.
slides where you went through quickly, I think you wrote Spiels as Spiel apostrophe S. It's Spiels.
Of course it is. Yeah.
Just if you use it again.
Yeah, thanks. No, I didn't think I'd have enough. I realized I have so much, too much material. But
I've done this a couple of times, and it's the same effect with it. If you do one, you have to do all of them.
yeah.
You can't say that, oh, and now I need this. Yeah, this is fundamentally different than what number theory does, where they first do the arithmetic layer and then you do prime factorization.
Yeah, I mean, I don't know if at the top there's a sort of algebraic number theory layer where it starts to get worried, but even then it doesn't seem to.
At least with what is done.
Yeah.
And I mean, that's the obstacle for that's why Sage works there so well.
Yeah.
Because they say, oh, this goes to the lower level. Like
Yeah, you don't.
the thing where we come in and say, oh, but why can't we do this? What do you mean? What on your bottom low level routine, you probably suddenly want to jump back up and call that routine from the other system.
Yeah.
You can't do that.
Yes, I need to think about what I'm going to leave out from the rest. Most of it. Well. Jupyter Notebook's working quite respectably now.
I mean, that is working consistently, and I mean, that's about 10 years ago. What I was trying to do is to get to such a setup. What I don't yet understand is whether what is now hidden behind localhost 888, whether this is something which is completely harmless, or whether this is something where potentially on a managed system, the system administrator says, what do you want to install?
On this system, it's actually running a gap process without any jail.
Yeah.
But there's no reason why it couldn't be running in a virtual machine.
Yeah.
It wouldn't be localhost 888 anymore, it would be something else. But
Yeah. To get to something.
Or
that
a
you
Docker
would-
image.
Yeah, that you would basically have a clickable installer, so someone who has just user access can run it.
yeah, you can set up a Docker
Because
that
I
just runs the whole thing.
I know, and Frank Liebeck felt, and the Financial Thomas, they felt very strongly this is the wrong interface, but that's the interface that people are accustomed to.
Yeah.
Eh,
There's also a very cute thing from Nicola Tilly called Thebe Lab, or Thebe, which somehow gives you a sort of lightweight version of this, where you just embed some JavaScript in your web page. It's not as interactive, but you can run the examples that are in the web page. But no, the remaining glitches are mostly to do with sort of view obj view string type issues. I mean, I'll come back to this if I have time, but the
yeah, and I mean that is okay. That is
Lovely, yeah.
in general something.
it's horrible. Yeah. Okay.
All right.
Right. Okay, so before I go on and talk about some of the system design things, to show you an example of what I was talking about. So, back to the same Jupyter worksheet. I'm just going to turn on some debugging in Gap so that we can see a little bit more about how Gap does things. Okay, anyway. You're not talking to me. Maybe it has. Okay. So this is our cube group again, and I'm making a clean copy of it, mainly so if I run this cell again, it doesn't just look up the answer it's already computed. And I'm asking it to find all the conjugacy classes of maximal subgroups, maximal subgroup class reps of the cube group. And I've turned on all this debugging, so it's telling me lots of things about how it does it. So it's using something called the TF method, which is in the slides I skimmed over. It's called the trivial fitting method. It's doing a whole load of computations here with subgroup series, normal series in solvable groups. This is another chunk of computational group theory I haven't had time to talk about at all. There's a whole theory for finite solvable groups. They're represented in a very neat, compact form. Computations with them almost always reduced to linear algebra, and so on. Eventually we end up finding some subgroup that we're interested in. We get to a smaller group. We carry on down, we carry on down. Now, what else do I want to pick out from this? Oh yeah, here. So it's been automatically doing a process very similar to what I started doing on the worksheet of finding subgroups and images and quotients and so on. I'm printing a rather randomly selected set of diagnostic messages about the way it's doing it. Here it says calling metax. The metax is the linear algebra software in Gap. The reasons for the name are historical. So it says it's asking for the characteristic polynomial of an 11 by 11 matrix. Now remember we started out here with permutations. So this is a concrete example of what I was saying. You can't do one thing without another. So what's going on here is that we've got the 2 to the 11 permitted flips of the edges. You can flip any 11 of the edges how you like, and that will tell you what the 12th one has to do. We're thinking of those as a vector space, and we're looking at the way that the permutations that move the edges around act on that vector space. Well, group acting on a vector space is matrices, and we're studying the representation theory of those matrices, which is admittedly not very complicated in this case. And we do some linear algebra to extract them, which doesn't take very long. And a bit further down, we'll do a similar kind of thing in characteristic 3 to get the action on the corners. Here, okay, more weird stuff. 1 co-cycles and 1 co-boundaries. This is homology theory. Why do we want to do homology theory, I hear you asking, or cohomology? Because that tells us about how the elementary abelian group that flips on the edges is stuck onto the permutation of the edges. It tells us about, of the various possible groups which have an 11-dimensional vector space acted on by this particular matrix group in this particular way, how many of them are there, and then we'll go on to work out which one we've got. Here we're doing the linear algebra in characteristic 3. This is the action on the corners, similar sort of thing. And now we're starting to paste together the different types of maximal subgroups which can exist. And in really quite a short time, we come out with this list of 20-odd conjugacy class reps of maximal subgroups. Here's the group itself, I think. Oh no. There's a lot of them. You could go on and explore their properties further if you wanted, but let's just do this maybe, which will... There are 20 of them, and that list is the list of the indexes of the maximal subgroups, so the index in the Q group. Okay, my real point there was simply to give you a concrete example, even for a relatively small example, doing what would until recently have been a fairly hard problem, just writing down all the maximal subgroup classes. A, we can do it very quickly and easily, and B, to do so, we need all kinds of bits of mathematics other than the one we started with.
May I just add one brief remark?
Yep.
What it also does is it uses the recognition. It finds at some point my group is an A11, and then it can't reduce anymore, and then it uses stored tables or information which basically is taken from the literature about maximal
Yeah.
subgroups.
That's exactly right. That was in some of the slides I had to skip over. The methods here rely on databases that describe the simple groups, as well as on linear algebra and other techniques to deal with the way that they're glued together. Okay, so I'm going to continue skipping over stuff quickly, I think, but I promised I would at some point say something about the history of GAP, so I should do that. 1985, development of GAP began at L'Echtel D in Aachen, and the leadership, the push to do it, the concept, the initiative came from Joachim Neubuser. The design was loosely modelled on earlier releases of Maple. He'd seen early versions of Maple with the idea that there was a relatively small kernel that implemented a language, and most of the mathematics was implemented in that language, and they very much adopted that philosophy. First release was in 1988. As I say, this was sufficiently before the widespread internet connectivity that release is a slightly nebulous term, but version 3.1 was released in 1992. That was the first version that really had extensive use of outside Aachen. Also in 1992, there was the first externally contributed extension package. So somebody outside the core development team contributed an extension to the system. 1996, we started attempting to organize refereeing of externally contributed packages. That's been, it's been useful and valuable and interesting, but not 100% successful, I think. It's difficult to find referees. It's been difficult to agree what the appropriate standards were. But the idea was both to give credit for the contribution and to maintain some degree of quality control. 1997, the first beta version of GAP 4, so this, as I say, was 21 years ago on Wednesday, was released following a complete rewrite, and Joachim Neubuser retired, and coordination of the system moved to Aachen at that point, to Andrews at that point. When I was preparing for this talk, I found this in my office. This is it's a CD, not a DVD, of the first 10 years of GAP. It contains all the versions of GAP that were released up until 1997, essentially, from Aachen. So 2.4, 2.5, 2.6, version 3, 4 beta 1. So that was the 10 years before the 21 years that we're celebrating on Wednesday. few highlights since then. 1998, 20 years ago, I spoke about this stuff at ISAC. Public release, or the non-beta release, the unqualified release 4.1. The beta was public, it just had a few caveats on it. 2004, control sort of diffused from St Andrews to an international group. 2005, longer ago than I'd thought, the first version of Sage, which included GAP, was released. So that's become a major channel for people to access and use GAP. 2008, we got Jenks Prize. 2009, we started developing a multi-threaded kernel. I'll come back to that if time permits. 2015, we took it to GitHub. There's a new German project, the Oscar project, which is building a system based on Julia that's linking GAP with 3 other systems. And just snapshot of where we are now. So the most recent release went out a few days ago, version 4.9.2. It includes the first version to include, or well, 4.9 was the first version to include HPC GAP, the experimental multi-threaded kernel, with fairly serious caveats. We're up to 137 externally contributed packages, which has given us some scaling problems that I might have time to talk about, but shows the level of interest. And increasingly the dynamic has been that interesting new functionality is in packages, and the evolution of the core system is primarily to better support the packages. Also in 4.9.2 is the Jupyter Worksheet interface I've been using. That's now available. Yeah, and that's today. Okay, so what I planned to do was to run through my 1998 ISAC talk and then talk about how some of the ideas in it have held up and how they haven't. I'm going to have to abbreviate that a little. So I've taken the slide. Well, most of what you're about to see on the yellow backgrounds are the slides from 1998, completely unchanged apart from reformatting. Anything in a box like that is a current comment. I should say that this, along with more or less everything else I've been talking about, is the work of very many people, but the mistakes and the opinions in particular are mine. Where I say that something is or isn't working out well, that's my view, and other developers in general will disagree with me. Okay. So, okay, this is a general introduction. I think you will have picked up most of this from things I've already said. At some point, we moved from our own license, which actually predates the GPL, to the GPL. We're still very careful about using. And one of the nice things about being GPL is you can pick up arbitrary GPL and LGPL libraries and use them. We're still quite careful about doing that because it gives us variations of DLL-HAL. Incompatible versions of things and getting things installed and maintained and whatever. There's a bit of C++ around, not in the core kernel, but in some extensions, but it's still basically a C system. Okay. Right. Probably the feature of GAP that was central to the talk 20 years ago, and is still probably the most unique thing about GAP, is the method selection system. So the problem with method selection is if the user asks you to do something like multiply 2 algebraic objects or compute the size of a group or compute the derived subgroup of a group, there are many, many different ways of doing that depending on what the objects are. So how do we represent and organize all those different ways of doing things and make the correct decisions, choose the correct methods for particular objects, while retaining some modularity so that we can change parts of the system, add new methods without having to change everything else, and being reasonably efficient. Okay, this is important. So, okay, I'm going to skip over a few slides that discuss other options. So we could just ignore, or very briefly skim over them. We could simply give every method its own name. So you'd have, integer multiply, rational multiply, permutation multiply, and the programmer chooses the method. Problem with that is you now can't write higher level functions that don't care how the multiplication is done. You can't write power by repeated squaring, for example, which doesn't really care how the multiplication is done, just what the power is. So you don't want to do that. It also makes the syntax unbelievably horrible. You could, I suppose, have a single multiply function that knows about every way of multiplying in the system. Basically some huge case statement could be invoked by infix star. That would give you polymorphism, but it gives you no modularity. It makes the system impossible to maintain or extend. Every time you want to do a new kind of multipliable object, you've got to make changes to this one huge procedure and all the other ones. So the classic solution to this is, of course, object-oriented programming. Every object in a system would actually or implicitly carry around with it all the methods that applied to it. And the operations would actually or implicitly look inside the object or its class or whatever for the methods. If you're in C++, you can resolve most of that at compile time. If you're in Java, you can't, whatever. And you gather the objects into classes. Objects in a class have the same method. This stuff is standard. And this was pretty much what GAP3 did. It's loosely speaking what Magma, Axiom, Java, C++ do. Why did we not do that? Two reasons, really. One is operations have more than one argument. And then the question is which of those arguments supplies the method. So in Java or something else, one of the arguments is in a special position. You say foo.multiply bar, and foo gets to decide what the method is. But that's not really natural. Multiplication is symmetrical. And it's particularly tricky if bar is of some kind of object that's introduced after foo. So you get various potential problems. The other issue that arises is that, as I hope you got the feel of from the cube example, you're often exploring objects. You're computing one thing about an object, and that tells you something, and then you go and compute something else. And what you already know affects what methods you can use. So what we'd like to do is, if we learn or compute something about the object, that changes what methods will be applied to it in the future. And there's no nice way in most object-oriented systems of doing that. So what do we do? Well, we have operations, which are essentially or placeholders for functions, virtual functions, and then methods that are the actual functions. And the difference between GAP4 and, say, Java is that the methods are associated with the operations and not with the object. So multiply is essentially just a great collection of methods of multiplying things together with some data structures that tell you which ones can apply to what objects. Okay, it doesn't matter very much. Yeah. And the general philosophy is that you choose the most specialized method which can be applied. Specializedness is not a total order. So sometimes there are two choices. My classic example is if you have a nilpotent permutation group, you may have a method for nilpotent groups and a method for permutation groups. And hopefully they'll both be correct, but which one of them will be faster is not something a system can be expected to predict. Okay. I'm going to very quickly, no I'm not. I'm going to skip the example because there certainly won't be enough time. Skip this because it's boring. So the choice of method is based on properties of the objects. And these properties are what we call filters. Filters are Boolean, they're just bits. So in principle, associated with every object is a bit string. In the current core system, that's about 3,000 bits. If you actually load every single package, it's something like 9,000, I think. Loading every single package is not recommended. And those are compared to the ones that are stored in the database, in the data structures for the operation. Obviously, we don't do that for every operation call. It will kill us. There's some caching going on behind the scenes. And the kind of information that those bits represent are what this slide is really there for. So we can say fundamental things about the object. It's a magma. A magma is anything with a binary multiplication with inverses. So I can multiply things. I've got a 1 and an inverse to do what I expect them to do. Here's another filter, has size. So this object knows its size. The size of this object is either stored or can be retrieved incredibly quickly. It's a particular kind of hash table. It knows whether or not it's abelian, which is important to distinguish from it actually is abelian. These are two different things. You can write a method for an object which knows whether or not it's abelian, and that will be called whichever of the two things it knows. You can also write a method for an object which is abelian. You combine fill, yeah, okay. So this is the mechanics. It's probably not interesting. This is more important. If you have a unary operation with no side effects, authentic 1998 typo. such as exponent that was in the example there. This is the exponent of a group. That has an associated tester, usually called has something, which tells you whether or not it's known, and another operation, the setter, which sets it. And the general idea is that if you call a method for the setter, it will store the value of the object attribute somewhere in the object, and it will turn on the tester flag. So the type of the object changes, different methods become applicable. In particular, a very fast method for that attribute that just retrieves the stored value becomes applicable. That's why I had to remake the cube group before doing the maximal subgroups, because that's an attribute. Once it's computed, once the result is stored, the second time round I wouldn't have had all those methods, I'd just have had one line that said retrieving the stored value. Yeah. Attributes are one of the things that's worked really well. In particular for objects where there are lots of different ways of constructing them and lots of different ways of getting to them, lots of different orders in which you might want to explore their properties. What you often do is to create the object with all of its data in the attribute. So you create the object, depending on how you created it, you set some of its attributes, and then you have methods that say, well, if it knows these attributes, then here's a method to compute this other one. Or you can say, okay, actually, in order to know this one, I need to know that attribute, so I'll just ask for it. You can say, do I know it? Or you can say, just go away and compute it. And those are nicely distinguished. And all attributes are remembered for most objects. So that's something that's proved very effective. There's a system, now what this can't capture, because the bits are essentially static, is relationships between objects. So I can write a method for computing a commutator that says take x and y and return x inverse times y inverse times x times y. But that could be called on any two things that can be multiplied and inverted. So in particular, it might be called on a permutation in a free group element, which would be horrible. And in order to deal with that in the method, you'd need a load of checking, which we're trying to avoid. But we can't build this in from the beginning because there are infinitely many different kinds of group element. I can make as many finitely presented groups as I want, and each of them, its elements are a different kind of thing. This is captured by a feature in GAP called families. Every object has a family. Equal objects are in the same family. And families you can create dynamically. You can make as many of them as you want. And you can do tests on the families as part of the method selection. And this is where I said all opinions are mine. This is one of the features that perhaps is a solution too far. It does solve the problem very nicely, and in certain places it's really helpful. But they're also can be extremely confusing, and since every object has to have a family, one of the most common questions you get asked by people starting doing GAP extensions is, I want to make my objects which are all of some nice straightforward kind. What's this family thing? And usually the answer is, well, just create a family, put them all in it and forget about it. And the fact you have to do that is rather tedious. So this is probably controversial amongst developers. This is maybe one of the things that was overkill. That's not interesting, that's not interesting, that's not important. What have I got? 20 minutes. So this is really an ad for a feature that's maybe underused. Amongst the things that was new in GAP 4 was the fact that you could make virtual lists and virtual records. So the operation that gets an element out of a list or puts an element into a list, lists in GAP are variable arrays, not linked lists, or the same for records, are operations, and you can install methods for them. So you can decide to make this object behave like a list. Most common thing is to have a virtual read-only list. So here's my infinite list of elements of this group. Well, you can still ask for the 935th one if you want, or the 27,000th one, whatever. This has been extended relatively recently, and this hasn't, I'm really, as I say, flagging this because it hasn't been much used. You can also install methods to make objects behave like functions. So if you have a GAP object like a homomorphism, and you'd like to just apply it to something by writing it as if it was a function, you can do that. And you can, the indexes in list access don't have to be integers, so you can basically treat them as dictionaries. And you can have multiple indexes, so you can have m square brackets 1, 2 by long-standing request. Okay, this was 1998. Okay. Things that have changed since 1998. Which of these are relevant? Talk about operation declarations. So I think I may already have mentioned we switched from our own built-in long integer to using GMP. That doesn't seem very momentous. It was our first experiment with using other GPL libraries. And I have to say, it was astonishingly painful. Maybe GPL was, this is partly down to the GPL maintainers, but trying to distribute the system for users on Windows, Macs, many flavors of Unix system, not always with root access, or the equivalent, and make sure that they had a version of GMP that actually was installed and compiled and worked with GAP and worked with the compiler that they were trying to compile GAP with, proved over the years. It seems to have stabilized now, partly because I think more people have it installed, but it was surprisingly much pain. It was not the good experience we'd have hoped. So we retain this direction of travel of cautiously depending on more GPL libraries, external libraries, mainly through packages. There are plenty of packages that install an interface to a library. But occasionally in the core system, we now use readline, we're thinking about zlib for file compression, a few others. But we're very cautious. We've added floating point. So there are built-in standard floating points, well, nearly standard. It turns out in standard IEEE 758 that a not a number is not equal to itself. In GAP, everything is equal to itself, and we decided not to break that just for the sake of relatively unimportant data types like floats. There is scope to add additional floating point libraries, and there's a package which adds a number of them. So you can add extended precision floating point, and an interesting thing is trying to work out what happens then to floating point literals. So suppose I have this little fragment of GAP. This is just a function that takes any argument and returns 0.2. Seems straightforward. The problem is which 0.2? If the user sets the floating points to be Joe's floating point library with precision of 100 decimal digits, before they read that function, which 0.2 do you get? If they set it between reading the function and executing it, which 0.2 do you get? You don't want to have to convert the string into a floating point literal every time you execute the function. That's obviously inefficient. So there's a whole complicated mechanism. So we also want the possibility that someone will come along with a new package and install a new floating point library. And that does actually work. So there is a design which you can look up in the GAP documentation. There's a default behavior which is to interpret it at runtime with the current library, but you can also put decorations on the literals. 0.2 underscore means interpret it when you read it and leave that interpretation forever. And you can put underscore at a letter, and there are different letters that mean different libraries. Various changes in the system, most of which matter here. But the direction of travel is to try and make the system more compatible with other things. So changes to make the garbage collector work alongside malloc, which it didn't used to. Changes to make it easier to link C and C++ libraries into packages, and so on. Okay. Briefly, some of the things that, in hindsight, are probably mistakes, at least in my view. And in my defense, I claim Einstein's quote, anyone who's never made a mistake has never tried anything new. These are unfortunately mostly things that are either incredibly hard to change because they're threaded all through the code, or incredibly hard to change because the users have got vast amounts of code that depends on them. So one thing that we cannot change, but in my view in hindsight is probably a mistake. In GAP, you saw this with the cube group. You define elements first and then make structures out of them. So we defined some permutations and then we made a group out of them. So all permutations, when you type them in, belong to the symmetric group on the natural numbers, and a permutation group is just given by its generators. This is great. This makes it very easy to get started, very easy to define things. Avoids a lot of ugly and complicated explicit casting. Magma takes the other view on this, and in the early versions of Magma, trying to cast every object into the right structure was a nightmare. Eventually they got enough of it implicit and automated that I think it's not a big problem now, but I was actually in Sydney at the time and it was horrible. What it does mean, though, is that you can't tell the difference between the trivial permutation group that only contains the identity permutation on 6 points or the one on 10 points. So I've got this group of permutations, none of which moves any of these 6 points, as opposed to this other one, none of which moves any of these 10 points. And in a sense, they're the same. In GAP, they are the same object. But there's a number of things you might want to do with them, like turn them into a list of images, that needs to know how many points this thing is supposed to move. And in GAP, you have to pass that as an extra argument to the functions, and it's clunky. Another example is that the symmetric group on 0 points and the symmetric group on 1 point are isomorphic, but they're not equal. In particular, their Reith product behavior is quite different. If I take the Reith product of S5 by S0, I get S0. If I take S5 by S1, I get S1. S5, sorry. And they're very hard to tell apart. Similar kinds of issues that arise are that matrices and vectors are just lists. They don't know implicitly what ring they're supposed to be over or what their dimensions are. The idea is you work it out from the entries. But of course, then you get problems like how long are the rows that this matrix has none of? So if I have a 0 by 10 matrix, no rows and 10 columns, I can't tell the difference between that and a 0 by 20 matrix. Nor can I tell what kind of entries these rows are supposed to contain. Is this a matrix of integers or of elements of the finite field of order 27 or something else? These lead to a lot of ugliness in actual programs. Okay, so that was one thing. I don't really have a solution to that one. I think it's a design decision so deeply baked into the system that we just have to live with it now, but it's clunky. Another thing is perhaps the perils of our own success. I remember saying, as we wrote some of the mechanisms for loading packages into GAP4, at which time I think there were 6 of them, if we ever have 100 packages, this is going to be horrible. We now have 137. It didn't seem like it was going to happen at the time. Essentially, the problem is that there's no isolation. There's only one namespace in GAP, and it's very easy for things that happen in one package to interfere with things that happen in another. Getting all the packages to work with one another again is probably the single most time-consuming bit of getting a GAP release out. It helps a bit, this is a feature I didn't talk about, but two packages can declare the same operation for different kinds of objects. And so long as you never install a method which could apply to both, you're fine. So that helps a bit. But you get other packages. Packages sometimes inadvertently change core system behavior, and then all the other packages break and all their test files break. We've spent a lot of time trying to come up with different solutions to this, different ways to break up the global namespace so that each package could do its own things and only interfere with other packages when it explicitly wanted to. But it seems to be very hard to marry that with the operations and methods concept. If I'm installing a method for multiplication, is this my own new multiplication I want to install methods for, or is this the system multiplication? And if so, then these types that I'm installing and those types that he's installing, are they the same types? The operation system kind of assumes a global world, and we haven't found a solution that we're happy with. Another annoying thing is that the order in which you load packages can matter. Yeah. Okay, I'll skip this one. I think it's relatively technical. Okay, so my final few minutes, say a little bit about the most recent, relatively recent things we've been working on. So this is attempts to produce a version of GAP that would let you use multi-core servers, multi-core computers basically, so to run multiple threads or multiple processes. A couple of historical things, the pargap, one historical thing and one other thing. The pargap MPI package that Gene Koopman produced, bound GAP to MPI, wrote a bunch of nice skeletons on it. It worked very nicely for some things. It never really got past what I might call the boring problems of producing a version of it that could be installed, started up, handled errors, shut down cleanly, got round the fact that at that time most users would have had access to multiple workstations on network rather than dedicated clusters. So, you know, the fact that Fred had set his machine up slightly differently from Joe and you had to use a different password to log on to Tom's machine, and it was just really ugly. It's no longer distributed anyway. Something that is out there and very much useful, but not what I want to talk about right now, mainly, is the SCSCP package. So, it's a remote procedure call mechanism, essentially. It lets you run a copy of GAP as a server and say this copy of GAP is providing these services to anyone who wants to use them, or to people who have the correct credentials and want to use them. You can use that to build distributed computations. You can use it to run database servers. You can use it to do a bunch of things. Data transport is OpenMath. That still exists, still very much supported by Alexander Konvalov. And it's effective for coarse-grained things. The cost of translating it into OpenMath, going through the procedure call, possibly going through some intermediate daemons or whatever, means you're never going to do very fast back and forth. You're never going to use it to multiply two integers. But if you're doing a database lookup or a relatively large chunk of a distributed computation, it works just fine. Error handling is still a bit of a problem, especially if one of the servers goes into an infinite loop. That's a ubiquitous kind of problem. Okay, and the thing I want to say a bit more about, because it's still kind of current, is the HPC GAP project. First thing I should say is it's a really bad name. The name is an artifact of who was involved in a project early on, but it's not targeting HPC systems. It's targeting big multi-core systems, essentially. So we want to support safe and effective multi-threaded programming GAP targeting multi-workstations and clusters. We had some money from the British government to get started on it. We have various smaller amounts of follow-on project. We had lots of people contributing there in time. The main name to mention here in terms of the technical design is Reimer Behrens, who's now at Kaiserslautern. And most recently it's been supported as part of the Oscar project, the people with Julia interface, because they would very much like, Julia is inherently sort of multi-threaded language, and they'd like to have a multi-threaded GAP. What did we have to do this? Well, we had to replace the garbage collector completely. The existing garbage collector wasn't thread safe and wasn't easily made thread safe. We've replaced it with BOEM, which seems to be a fairly standard, good quality, free open source garbage collector, and it's stubbornly slower than our own. We've not yet managed to get it to within about 15 or 20% of the performance of our garbage collector for many single-threaded computations, which is a bit annoying. We had to do we had to do the obvious thing, which is we had to re-engineer the GAP interpreter so you could actually have multiple GAP interpreters running concurrently in all the different threads. That's quite a lot of work, but nothing particularly special. And we had to do something about a user interface. Still a bit of an open book, this one. If you've got multiple threads running and they all want to do I/O, what do you do in the context of an interactive system? You either get all the output from all the threads at your console, which is a pain, or all the output from the other threads goes somewhere else, then you don't realize it's there. Welcome thoughts. Also, I mean, roughly speaking, the question is, what should a multi-threaded read-eval print loop interface look like? If I type something, which thread gets it, which thread handles it, where do I see the results? What happens if I change the current thread while it was calculating, and so on? Supplied a bunch of concurrency primitives for the programmer in GAP, probably too many of them, but let's see which ones people like. The most developed of them is a task farm model. And because of the nature of GAP, it's essentially impossible to avoid lots of concurrent access to shared data structures. Alexander mentioned that in order to compute the maximal subgroups of the cube group, we had to look up databases about properties of S11. So first thing we would get our standard copy of S11. There's only one of those. Every time someone computes something about it, it acquires another attribute. It doesn't really change. It doesn't cease being S11. But it's acquiring information, and that involves changing the actual data structures and a bunch of other things. So it's probably the most interesting bit of it. There are lots of reasons why people update globally visible data objects in GAP code. And one of our goals was not to have to throw away the several million lines of the GAP library and write a completely other one. So we need to make existing code more or less work in threads, at least where it's not explicitly and unavoidably unsafe. Okay. Yeah, so storing attribute values, caches. There are a few other nasty things, like back in 1997, it seemed like a good idea to say, oh, we've just realized that this list of characters is actually a string, so let's convert it to the compact representation of a string, here and now in place, so that it'll be a string for the future and be faster. That sort of thing is not good if someone else is accessing it. We didn't want to force the programmer to just avoid everything which could do that, because that basically stops you using GAP, stops using any of the library anyway. So we need to support some of it and check the safety of the rest. And again, now I'm going to switch to just using one way of moving between slides. Okay, so I mentioned the task farm. I'm not going to stop now and look at the functions. The data access control, I think, is the most interesting thing, so I'll use my last couple of minutes to say a little bit about that. Every object in a HPC gap session is one of 4 different things, apart from a few very weird ones. It's either thread local, so one thread has created it, that thread still owns it, no one else is allowed to access it at all. So there's a very quick check if you access a thread. If it's thread local to you, you can do what you want, so that's fine. Most objects start out that way, but you can migrate them to other states. An object can be read-only. Some objects are inherently read-only. No thread can write it at the bit level. So the object is literally read-only. The data structure never changes. Stronger than immutable. It can be public, which means all the gap-level operations on it are atomic, they're safe. So the kernel code deals with whatever locking is needed. Things like groups are of this kind. So if one thread installs an attribute in a group, another thread will either not see it or will see it, but won't see it half installed. They won't see the data structure in a broken state where it's been half installed. It's still possible to program mistakes with atomic objects, it's better. And then you have explicitly shared objects that have to be locked in the gap code, and you can have multiple threads with a read lock or one thread with a write lock, but not both. And those are used only when you really want to explicitly have something that you're dealing with locking on, that is where your threads are communicating with each other. All of this is enforced in the gap kernel, and most of the necessary checks are actually automatically added to the C code. It's not perfect, it doesn't make it impossible to write broken multi-threaded code, but it does make it harder. Okay, as I said some time ago, I'll put all of this on the web somewhere so you can look at the examples there. Status of HPC gap, to finish with, well, it mostly works. It's not perfect, it's definitely an experimental release. Most of the library code and quite a bit of the package code will run everything will run normally in the first foreground thread. The problem is that you find some object is still thread local to the thread that read the library and hasn't been migrated to something else. And so when you try and run something in a background thread, it can't access it. That doesn't happen very often. It's mostly easy to fix it, but it's also easy to break it again. As of this moment, Ward is broken, but we're working on it. You take the performance hit from the garbage collector. And in order to get any real speed-ups out of it, the programmer still has to take responsibility for sorting out task granularity. If you make the tasks too small, all the time is spent doing the task management. If you make them too big, all the time is spent doing the last one. So, pays your money and you takes your choice. That's where we are. So, it does work. Things can get faster with using it. At this point in time, it's either hit or miss or takes some work. We're very much welcoming anyone who's interested in experimenting with or communicating or contributing to it. Okay. And yeah, I'll put this up, but there's some references and things. Okay, so that's my time. Sorry, it was even more of an abbreviated skim over things than I'd designed it to be. But anyway, thank you. I'm not really the right person to answer that because it's a DFT-funded project, and the gap-related partners to this is Frank Liebeck in RWTH Aachen. My understanding is that it should be possible to call more or less arbitrary gap functionality from a Julia program, and presumably to mix it with functionality from the other systems, Singular and I can't remember what the other two are. And also to write gap kernel functions in Julia. So a function written in Julia which potentially calls one of the other systems can be called from gap just like a kernel function that's written in C. That's my understanding. I could be wrong.
So I got the impression that you first intended to have a distributed computing support, and then quitted that idea and only focused on the shared memory prioritization. Do you still plan to support distributed computing in the future, or is it something?
Well, I mean, SCSCP is actually a fairly effective distributed support for coarse-grained things. There's no active, I mean, it would be nice to have a distributed system that let you actually program with distributed data structures. That was really the bit that was interesting for distributed things, to say, okay, I've only got 128 gig of RAM on this machine, but I've got 24 machines, so I want to define a 3 terabyte data structure that's distributed across the machines and program with it in some sensible way. We didn't get very far down that road at the time, and while it might be something interesting to revisit, there's no one currently working on it.